let's get started on the last problem of section 1 in chapter 3. We work on gamma naught of p first. I have to prove that there are only two cusps. So let's, we actually already worked on this guy in problem 14, where we should describe the fundamental domain of gamma naught of level p. Actually, I didn't do that. I only did it for level 3. We'll need to do that work while I failed it. So first I'll write up the generators of the cosets, which we have from problem 14. E is unity to go, k goes from 0 to p minus 1. That's p. And the index, we already know that to be psi of p, which equals p plus 1. All this have been covered in the previous problems. And this is, so we're lacking just 1 from the other family. So that's from 1 to, when p is 1, this is 0, so there's none. Oh, there's unity, of course, too. That's the trivial one. So altogether p plus 1 matrices. And that is the fundamental domain is the, oh, I can't call it F. F naught of P equals F, and then the union of all of these guys, S T to K of F, for k going from 0 to p minus 1. And this is easy to describe. This is just a parallel translation of f. So it still only has the cusp at infinity, and they are all connected. I'll just draw them. So we have the cusp at infinity, and then we must map S. When k is 0, we go down here, so we'll just make the blue one. That's a poor color. Red one should be able to see. F itself. SF, and then S of all of these, they will be connected and only having the one cusp. So this point is, and then we'll have a guy down here and another guy down there. So that'll be the general form. So we only have the cusps at 0 and infinity. So we need to show that they are not, that they are distinct. And we could do that explicitly, the way I did in problem was it 16, I think? Or we can use, problem 17. Oh, they call it J, that for some n, this should lie in gamma naught of P, where this is the one having infinity. That means it's the identity. And these are one of these. Having the cusp at naught. And we have the guilty party here. That P divides 1 is impossible. So that means that we do have two cusps. That was A. Now B, that becomes a little more technical. We have this family which goes on to P squared minus 1. Oh, let's first do the index. So it's P squared plus P. We have unity. We have T to Ks, or minus Ks, where K goes from naught to P squared minus 1. So there's 1, there's P squared. And then here we go to P, from 1 to P minus 1. K going from 1 to P minus 1, that gives P minus 1. So the total agrees. I wonder what this does. Of course, we already know what this does. This gives something like this, but then we get something like this. So it's just bigger than this. Oh, this is actually larger as well, so I'll just write it up. These only have the cusp at naught. We need to find the cusps of these guys. that must be done explicitly. This is mapped to naught. So this is mapped to Kp. And that's -1 divided by Kp. I wonder if that's simply connected. But never mind that for the time being. So that's the possible cusps for k going from 1 to p minus 1. Yeah. We need to show that they disagree altogether. So first let's check that they disagree with all of these guys. Is one trivial as well? Yes, I think so. This is the guy we need to work on. S t to k plus n s t to minus lp s. I need just to check what we can do here. We should be able to move this s out. But I have to find out how to do that. It seems the only reductions we have is that st to the third and ts to the third equals minus the unit matrix. That doesn't help us. This means that I'll make this matrix multiplication in Mabel. And we need to compare these guys. Yeah, we don't need to compare these with themselves because we already covered that. It will be the same. So we need two of these guys. Oops, there was a t to the nth in here. So that's s t to lp s t to nth s t minus kp s. That calls for the break to make Mabel do that. I had to define this as the power as a function, otherwise Mabel didn't want to compute t to some power, all right. And then we get this and modulo p, it's equivalent to -1. So it can't be naught modulo p squared, can it? I really don't see that. Now down here, this is p squared, so it's k minus L times p. So something, and here we have k minus L times p. K is smaller than p squared. Oops, which one is k? Now I should have used distinct. Oh, yeah, they both go from 1 to p minus 1. And of course, if they are equal, p may divide it, but they had to be distinct, of course. And then p doesn't divide the difference. We've had this before. I would actually like to make a low-level reasoning. If we have two numbers, k point L, going from naught to p minus 1, then we can't have p dividing k plus L, or k minus L. This is not quite, I didn't reason quite clearly why that is so. Of course, the result is smaller than p, because it's smaller than or equal to p minus 1. And if it's naught, then they're identical, and it's larger than p minus 0. So it's simple. I just didn't take the time. I did take the time doing the details, but I didn't take the time previously to explain it properly. I believe this concludes section 1.